Hey, this is lesson 14-1. This is an introduction to trigonometry, but I want to start by reviewing some of the basics of functions. And I hope you learned a little bit about the idea of functions in first year algebra so that this stuff rings a bell. If none of this rings any bell at all, you're going to be okay without it. But if you do recognize some of this stuff, I think it will help make a little more sense out of what we're talking about today. So when we write a function in mathematics, we start out with something like this: f of x, some function of x equals 2. And then we provide the algebraic rule for x. And so the rule might look something like this: x squared. And this variable defines the input to the function. And then this whole expression on the right defines the output to the function. And again, if this is the input to the function, then this is the rule for the input. What are you doing to the input to get the output? You're squaring it. So squaring is, in a sense, a function. But you can have all different kinds of functions. Right? You can have f of x is equal to, the function could be double the input value and then add 5 to it. So that's a more complicated function because it has multiple steps to it. Square rooting can be a function. F of x is equal to square root of x. Now, depending on what kind of calculator you're carrying, if you want to take the square root of a number, when you press the square root button, you might also get a parenthesis appear. Your calculator may just automatically throw a parenthesis up. Some of the older Model TI calculators always did this, routinely did this. And maybe some of the less expensive calculators still do this sort of thing. And you might have wondered, why is it putting a parenthesis up there? If I want to take the square root of 16, why do I need a parenthesis for the 16? Well, you don't need a parenthesis if you just want to take the square root of 16. But suppose you want to take the square root of 985 plus 172. Well, you got two ways that you could do that on your calculator. You could do this addition first, get a result, and then put the result in the square root. So do it in two separate steps. Or you could do it like this: surround the 985 and the 172 in parentheses, put it in like that. Now the calculator will do exactly this for you. If the calculator didn't put that parenthesis up and you didn't know that you needed to put this in parentheses, if it just put up a square root symbol and you put in 985 plus 172, what the calculator would do is it would take the square root of 985 first, then it would do the adding. Okay, so square rooting is a function, and the calculator has a way of indicating that something is a function by throwing up a parenthesis and saying, all right, what do you want to put into the function? You don't have to put just a single number. You could put a whole collection of numbers that are being multiplied, added, subtracted, divided, squared, whatever, before you actually then take the square root of all that stuff. Now, a more current version of a graphing calculator is more likely to behave like this. When you hit the square root button, you get this, and the cursor shows up inside the square root button. And the more stuff you type in there, the longer and longer the square root bar gets. And so what if you wanted to do something like the square root of 225 and then plus 3, but you didn't want that 3 inside the square root bar? Well, then you've got to do something to get out of this square root bar, maybe hit the right arrow key or something like that, so that the plus 3 ends up outside the square root. Anyway, this lesson is not about square roots. It's about just, it's not about functions in general, but we are talking today about 3 functions that you probably have never heard of before. And they have names. I mean, we've talked about squaring, square rooting. These are ways of describing functions, right? These new functions have names. And the names are sine, cosine, and tangent. Those are the full word names of these three new functions. And because they are functions, anytime we want to use these functions, we need to have a parenthesis and indicate what is the input to the function. Okay. Now, we typically abbreviate these words down to three-letter abbreviations, but we still pronounce them as if they were spelled this way: sine, cosine, tangent. When you're reading an expression like this out loud, don't say sin. Sin is not a bad word, okay? But it sounds like you don't know what you're talking about. Nobody who has learned trigonometry says sin of an angle, okay? And we'll say cosine. Don't just say cos or cos or something like that. And don't just say tangent. That's just how people speak when they're reading these expressions out loud. So please try to adopt that way of speaking as soon as possible so you won't sound like you don't know what you're talking about. Also, the way we read an expression like this is sine of an angle, and you got to get used to that also, okay? Because, for instance, if we had an expression like this, we might read that as 5 times a. That would be an appropriate reading of that expression. 5 times a, or even 5a, if we were kind of simplifying it in our head. Okay. But when we read this expression, again, if you learn anything about functions, you recognize, oh, that's not f times x. We say f of x. And likewise, consider the square root function. How would you read an expression like this? You would say square root of 17. You would not say square root times 17. That makes no sense at all. So this expression, the way we read it is sine of angle, or the sine of an angle. Okay, now what does the sine of an angle mean? Okay, I've written out the definitions for you right here of these three new functions: sine of an angle, cosine of an angle, tangent of an angle. First of all, before we talk about what it means, notice that the input value to any one of these three functions is regarded to be an angle measure, not just a number, but a number that represents an angle measure. You must have an input to these functions always, and the input always 100% of the time must represent an angle measure. Okay? So now let's move on to what the definitions of these three functions are. The way sine of an angle is calculated is by imagining that angle existing in a right triangle. And now let's talk about that for a second. If we're imagining a right triangle, besides the right angle, the other two angles then must be acute angles. You can't have an angle that's larger than 90 degrees fitting into a triangle that already has a 90-degree angle in it. And so these angles must be acute angles. I'll say more about that again in a little bit. Okay, so imagine this acute angle as part of a right triangle. Like in these triangles here, we've got some acute angles in these right triangles. Oh, I'll say more about the definitions in a little bit. I think what I ought to do is read through this stuff for emphasis here. First of all, these expressions: sine, parentheses with nothing inside, cosine, parentheses, tangent, parentheses with nothing inside. Those expressions by themselves do not have a value, okay? Just like the square root symbol without an input into it does not have a value. Square rooting is a process. You can think of it as a way of getting to a particular result, okay? Sine and cosine and tangent are ways of getting to a particular result, but you don't have a result if you don't have an input to the process, okay? So there must be an input value, and the input value must be an angle measure, as I was just saying, or it could be a variable that, again, represents an angle measure. And for this course, for geometry courses, almost always, universally, when you're learning trigonometry in a geometry course, the angle must be an acute angle. We're not going to be putting 90 degrees into any of these three functions. Now, in later math courses, possibly next year in Algebra 2, you will learn how to find output values for these functions when the inputs are 90 degrees and larger. Such things do exist, but you're going to need to learn different ways of defining these functions than the way we learn to define them in a geometry course. Okay? So, the way, getting back to the definitions themselves, the way these, I shouldn't scribble there, the way these functions are defined is the sine of an angle. Imagine the angle as being one of the acute angles in a right triangle. Take the side length that is opposite from that angle, divide it by the hypotenuse in the triangle, and that result is the value of the sine of the angle. We're going to talk about what opposite from that angle means. Okay? The cosine of an angle, that result is found by taking the length of the side which is adjacent to the angle and then dividing by the hypotenuse. We're going to talk about what that word means, although I'm sure you've heard it. Okay? And then the tangent of an angle is found by finding the length of the side which is opposite from the angle, just like over here, and then dividing by the side which is adjacent to the angle, which is the same as that adjacent side there. So all of these functions, sine, cosine, and tangent of angle measures, can be thought of as ratio functions. Their output is always a ratio of two side lengths of a triangle. Okay. I'm sure you've heard the word adjacent before. It means next to. Okay. I don't know how many of you have had driving lessons yet. Probably not many of you, but if you're getting a driving lesson and somebody tells you to pull into this parking lot and park adjacent to that yellow car over there, adjacent means next to. You pull up next to that person. If you're sitting adjacent to somebody in class, you're sitting next to, alongside them. Okay? If you've got four people sitting around a table, A, B, C, and D, you could say that person B is sitting adjacent to this person and adjacent to that person. But you would say that person B is sitting opposite from person D, or across from person D is another good way to think of opposite, directionally, across from, as opposed to next to. Notice person B is sitting adjacent to two different people in this situation here. Right? And we're going to encounter that ambiguity in this example here. So let's come up with a value in this first example here for the cosine of 60 degrees. Okay, so we've got a right triangle with a 60-degree angle in it. We've got two of them, actually. And here's a 30, 60, 90 right triangle that you should be very familiar with back from our studies of special right triangles and similarity, right? If you've got a right triangle with a 60-degree angle in it, the other one's got to be 30. And all 30, 60, 90 right triangles are similar to this one in particular. We kind of use that as our reference point, okay? So here's another 30, 60, 90. Where the ratios of corresponding sides are all the same. The ratio of this side over that side is 5/1. And the ratio of the hypotenuse over the other hypotenuse is 10/2, which is 5/1. And the ratio of this leg over this leg is 5√3/5. No, excuse me, not over 5, over radical 3. And what does that simplify to? Well, the radical 3's cancel out. It simplifies to 5/1. All the ratios of the corresponding sides are all the same, and that's what makes these triangles similar to each other. Okay? So, the cosine of 60 degrees. We can go to either one of these triangles to get the answer or the value of this expression. this function, cosine, with an input of 60 degrees, we're going to get the same value. It doesn't matter which triangle we go to. Okay? Cosine of 60 degrees. We got to find the side in the triangle which is adjacent to the 60-degree angle. Okay? And then divide that by the hypotenuse of the triangle. So imagine that this triangle is rather large. Say it's laid out on a street or on a huge expanse of pavement, and you're standing right here at the corner or the vertex of that 60-degree angle, and you're looking out at the triangle. Okay? The one side which is opposite from that 60-degree angle, or across from that 60-degree angle, is this side over there. You would sort of run through the middle of the triangle, through the open space of the triangle, until you got to the opposite side. That square root of 3 would be the side length which is opposite from the 60 degrees. Which is the adjacent side? Well, again, sort of like somebody sitting at a round table, person A sitting adjacent to person B and person C. There are two sides of this triangle that are right alongside you, right next to you where you're standing. You're standing here at the vertex of the 60-degree angle. You're standing at one end of this side of the triangle, and you're standing at one end of this side of the triangle also. In a sense, they could both be considered sides that are adjacent to the 60-degree angle. They are the two sides that are being used to form the 60-degree angle. So they are, in a way, listen to me carefully, I'm saying they are both, in a way, adjacent to the 60-degree angle. But for purposes of this conversation, what we mean by the adjacent side is only the side that I've left traced in red. We would not consider that side whose length is 2 to be the side which is adjacent to 60 degrees. And I wonder if you could guess why. Somebody usually can guess when I'm in the classroom. And maybe you've guessed correctly now. The reason is because that side, which has a length of 2, is the hypotenuse of the right triangle. Okay? And so we never, ever consider the hypotenuse to be the adjacent side. Always consider the adjacent side to be the other side that you're standing next to, not the hypotenuse. You see, we've got the hypotenuse in 2 out of these 3 definitions. Adjacent side must mean something else, not the hypotenuse. Okay? So, cosine of 60 degrees, it is the adjacent side. Here's the 60-degree angle. We're standing right there at the vertex of the 60-degree angle. 2's the hypotenuse. It can't be the adjacent. 1 must be the adjacent side. And then divided by, here's the rest of the definition, divided by the hypotenuse length. And the hypotenuse length is 2. So there's the value of the cosine of 60 degrees. It's 1/2. You could write it as a decimal, 0.5, but don't, okay? Do not waste 1 second turning perfectly good fractional answers into decimals. Don't do it, okay? In many cases, in some cases, I will ask for exact values for these expressions, okay? And if you resort to using a calculator, you may very likely come up with a decimal value that does not terminate, it goes on forever, and it does not repeat, and you cannot write the value exactly as a decimal. And so you should just leave it as a fraction, okay? Tangent of 30 degrees is the next thing that we're being asked here. Tangent, where's that definition? I'm trying to get my eraser to clean up some of this work up here. tangent is over here. It's the opposite side divided by the adjacent side. Tangent of the angle, in this case, the tangent of 30 degrees. So we want to go position ourselves at the vertex of the 30-degree angle, right down there in that corner, okay? So which side is the opposite side? The one that is most removed or farthest away from that 30-degree angle. It's the one that you would get to by running through the center of the triangle across to the opposite side. That would be a 1. Right? And then divided by the adjacent side. Okay, and I've already used the opposite side. The adjacent side must be one of these two. But which one? I mean, they're once again, they're both used to form the 30-degree angle. They are both, in a way, next to or alongside of or adjacent to the 30-degree angle, but one of them really isn't the adjacent side. If you've been paying attention, you know the 2 is not the adjacent side because the 2 is the hypotenuse. Okay, and so the adjacent side here is the square root of 3. And there is a perfectly accurate value for the tangent of 30 degrees. But this is not in simplified radical form. Do you remember that? We don't allow square root signs in the denominator of a final answer if we want that answer to be in simplified radical form. Do you remember how we deal with that? We got to multiply by the square root of 3 over the square root of 3 and then carry out that multiplication. 1 times the square root of 3 is the square root of 3. And the square root of 3 times the square root of 3 is the whole number 3. I mean, it would be the square root of 9, but that's the whole number 3. And we want it to be a whole number, not a square root number. That's the whole purpose of doing this, is to get rid of the square root in the denominator. So this is the exact value in simplified radical form. It's the same value as what we started out with here. Okay, trust me, put either one of those expressions in a calculator, you'll get the same decimal result. Okay, but the decimal result is a non-terminating, non-repeating number. Okay, and if I ask you for the exact value of this expression, and you give me anything other than this or this, you're probably not giving me the exact value. You certainly cannot write it as a decimal. Okay. Now, before we leave these two examples here, I just want to go back and reinforce the idea that we could have used that triangle on the right here to get the value of these expressions, and ultimately we'd come up with the same results. Okay? Let's use this triangle on the right to get cosine of 60 degrees. The cosine would be the adjacent side, which is not the hypotenuse. It would be the 5 divided by the opposite side, which is, cosine is the adjacent side divided by the hypotenuse. That's what the definition says. Adjacent divided by the hypotenuse. 5 over 10. Well, that reduces to 1 over 2. So we get the same result. Okay. Same thing with the tangent. If we had used this second triangle, we would have gotten 5 over 5 radical 3. The 5s would cancel out, leaving you with not radical 3, but a 1 over radical 3. So we get the same result. Okay. So the cosine of 60 degrees is always and forever the value 1/2. And it doesn't matter what 30, 60, 90 triangle you use to calculate that value, it's always 1/2. The tangent of 30 degrees is always this value. Okay. One other thing I want to draw your attention to before we leave these two examples, and maybe try a few of these sorts of problems on your own. Let's talk about how both of these definitions, cosine and tangent, use a reference to adjacent side, right? Cosine references adjacent side. Tangent also references adjacent side. Okay. But the phrase or the term next to kind of has a Well, let's just go to the problems. 60 degrees. Which side is adjacent to the 60-degree angle? It's this one here. But in this problem, we're talking about the 30-degree angle. And which side is next to or adjacent to the 30-degree angle? It's this one here. Okay? So the adjacent side of a triangle, that expression right there, quote, the adjacent side of a triangle, end quote, that expression makes no sense. Okay? Either one of the legs of the right triangle, not the hypotenuse, but either one of the legs could be the adjacent side. It depends on what are you supposed to be adjacent to. Okay, what are you next to? If you're supposed to be next to the 30-degree angle, that's one side of the triangle. If you're supposed to be next to the 60-degree angle, that's a different side of the triangle. All right. I say this because sometimes students get it in their heads that the opposite side is always a particular side of the triangle. Like it's always the short side, or it's always the long side, or it's, God forbid, it's always the hypotenuse or something like that. Okay. There's what we call a relativity, a relativeness. It's sort of a depends. Adjacent depends on where you're starting from, and opposite depends on where you're starting from. Okay. If you and I are facing each other and I say, who's the person who's opposite the other one? That question doesn't make any sense. We're both opposite from each other. If I say who's opposite from me, the answer is you. If we say who's opposite from you, the answer is me. Okay. All right. So let's go down and try some examples. Seriously, pause the video. See if you can come up with answers to these 6 questions right now. Pause it. Wait, don't do that. I should tell you one other thing. I almost forgot. There is a memory device that students have been learning forever to help them remember these 3 definitions. Now, you're not going to have to memorize these 3 definitions because since we're doing everything remotely, you can always refer to your notes and you can look everything up. Okay. Still, you want to learn this memory device because everybody learns it. And next year, when we're all back in the classroom, and the year after that, you're not going to be able to refer to your notes and you're going to need to know these definitions. So learn them now, learn them sooner rather than later. Okay. Here's the memory device. We take the first letter of the word sine, opposite, hypotenuse, cosine, adjacent, hypotenuse, tangent, opposite, hypotenuse, in that order. Sine, opposite, hypotenuse, cosine, adjacent, hypotenuse, tangent, opposite, adjacent. And then we string all those letters together without the dashes, SOHCAHTOA. And that word is generally pronounced SOHCAHTOA. Okay. And everybody remembers how to say it, SOHCAHTOA, but you need to know how to spell it. Because if I hadn't shown you this word and I said, hey, everybody grab a pencil and spell the word SOHCAHTOA, which you would have never heard of in your life, I probably would have gotten 15 different spellings. Okay. The spelling matters because the spelling is intended to help you remember that the sine of an angle is calculated by dividing the opposite by the hypotenuse in that order. Opposite divided by hypotenuse, not the other way around. You know, the order of division matters, right? And then the cosine is equal to the adjacent divided by the hypotenuse. And then the tangent is equal to the opposite divided by the adjacent. This 9-letter word kind of comes in 3-letter blocks. And each 3-letter block helps you remember the definition of one of these 3 new trig functions. SOHCAHTOA. That's how we say it. Okay. Now, if I just write that abbreviation right there, or that we call it an acronym, actually. An acronym is a word whose letters all are the beginnings of other words. There it is. SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Now, pause the video and try to come up with the correct answers to these 6 questions. All right, so sine is opposite over hypotenuse, but we're starting from angle P's point of view. From P's point of view, the opposite is 15, and the hypotenuse is 17. Okay, now the hypotenuse is the hypotenuse from any point of view on this triangle. Okay, but the opposite from P's point of view is 15. I'm going to jump over to problem number 6. Okay. I wanted to erase. I'm not going to jump over to problem number 6. Let's do cosine of angle P. Again, from angle P's point of view, cosine here is adjacent divided by hypotenuse. I know the hypotenuse is 17. What is the side which is adjacent to that angle there? Is it the 8? Well, it could be the 17. They're both next to the vertex of that angle. But no, it can't be the 17. Right? It has to be the 8 because 17 is the hypotenuse. So there's the value of the cosine of angle P. Tangent of angle S. Tangent is opposite over adjacent. That's what SOHCAHTOA reminds me of. From S's point of view. Okay, now we're jumping over to this corner of the triangle. The opposite side is the 8, and the adjacent side is not the hypotenuse, can't be the hypotenuse, it must be the 15. So there's those first 3 values. Cosine of angle B. Now we're talking about this triangle over here. What is adjacent to angle B? It's the side whose length is given to be lowercase a, divided by the hypotenuse, which is given to be lowercase c. Tangent of angle A. Let's jump over to angle A now, and the tangent is opposite over adjacent, opposite over adjacent. From angle A's point of view, the opposite is lowercase a, and the adjacent is lowercase b. Sine of angle A. All right, from angle A's point of view, sine is, SOHCAHTOA tells me it's opposite over hypotenuse. The opposite from angle A is side length A, and the hypotenuse is C. There's your 6 answers to those 6 questions. Some of the homework problems are going to ask you questions as short and simple as these. Just go to the triangle, make sure you're choosing the right sides and write the ratio, and do not waste any time changing any of these into decimals. Okay, leave them as fractions. These would be nasty decimals that, although they would eventually repeat, some of them, you probably can't even tell where they're repeating. The 8/15ths, that one you could tell where it was repeating. But don't do it. Leave the answers as fractions. You're wasting your time. Okay, and you're not getting a better answer by punching it into your calculator and trying to read the decimals. Okay. All right, there are some other problems on the homework that look like these on this page. Okay, and they're a little bit more involved. Excuse me. So for number 7, for instance, let's find the sine of angle F from the triangle below. All right, what's my memory aid? SOHCAHTOA. SOHCAHTOA. Sine of angle F right here, these 3 letters. I need the opposite side from angle F, and I need to divide that by the hypotenuse. Here's angle F. Put yourself on angle F. Okay. Now, the hypotenuse is the hypotenuse from any point of view on this triangle. So I know the denominator of this answer is going to be a 25. The opposite side is this one. There's no value given there. But some of you probably are recognizing quickly, we could find that value, couldn't we? This is a right triangle. We have 2 out of the 3 sides. What can we use to find the one missing side? Pythagorean theorem, right? So label it something, call it A, B, or C if you want. You probably wouldn't call it C because in the Pythagorean theorem, C usually stands for the hypotenuse. Call it X, call it Y, call it whatever you want. X squared plus 24 squared is equal to 25 squared. Do the little bit of work required to solve for x. It's not much. You'll find out that x is equal to 7. Okay, and that's the side that is opposite from angle F. And so the sine of angle F is equal to 7/25. Okay, so a little Pythagorean theorem work required to solve this problem. Not complicated, not a big deal. Okay, we could run right on to the next problem, but I want to point out something to you that I'm probably going to have to say a lot over the next 2 lessons, and I'm going to start saying it now. Notice what we have come up with a value for is the sine of angle F. If you put just 7/25 as your answer, fine. I'm going to give you credit. That is the value of the sine of angle F. Okay. But I want to point out that if you write something like this, sine equals 7/25, that expression there, that equation there, makes no sense. The letters SIN without parentheses and an input is meaningless mathematically. Okay, so this would be bad. I rarely see students write that. Okay, but occasionally, in rare instances, they do. Sometimes I see students write something like this. Rarely, but occasionally I do. Again, sine without an input value is meaningless. This would be bad. Okay, but students usually don't write those 2 bad things. Here's what they write very commonly that is really bad and really wrong. They'll write angle F equals 7/25, or maybe just F equals 7/25. That would be really, really bad and wrong. Okay? We don't know what the measure of angle F is in this problem. Okay? It hasn't been given, and we're not finding out either what the number of degrees in angle F is. We came up with this value for the sine of angle F, 7/25. That came from the lengths of the 2 sides in a ratio. Okay? We did not find the measure of angle F. And I'm telling you, over the next 2 lessons, some students will get to fooling themselves into thinking that what they've come up with here is the measure of angle F. And if any of you are thinking, well, that's silly. How could an angle measure be 7/25? Well, it could be. There's absolutely nothing inherently wrong with an angle measure being 7/25 of 1 degree. I mean, that would be a super small angle, but there's nothing inherently wrong with that number. It's just that that number does not, in this case, represent the size in degrees of angle F. Okay. At which point some of you might be asking, so what, well, then what does it represent? Well, so if you're legitimately asking that question, it's a little bit hard to answer honestly, other than to say it represents the ratio of 2 side lengths in that triangle. And we're just going to leave it at that for today. Okay? Don't write a decimal value for that. Problem number 8. I got a triangle that I've drawn for the problem. It's got an angle B in it, which is referred to in the question here, but I haven't put any numbers in this triangle. Okay? How am I going to find the cosine of angle B when there are absolutely no numbers in this triangle at all? This is what I'm being asked to find. Find the cosine of angle B, which again is going to be the adjacent side over the hypotenuse, referring back to SOHCAHTOA. Right? And here's angle B. But from angle B's point of view, I don't know any of the side lengths in this triangle. Okay, well, some of you may have noticed that we've been given some information about this angle B. What you have to learn to do right now, because there are about 3 or 4 homework problems like this, you got to learn to insert this information about angle B into the picture of the triangle. Okay. That's how we're going to then be able to find the cosine of angle B. Recall from this word here, using this three-letter block, that the sine of an angle is determined by dividing the opposite side length by the hypotenuse side length. And so these numbers can represent side lengths in the triangle. The 5 is the opposite from angle B, and the 13 is the hypotenuse. So put the 13 alongside the hypotenuse and put the 5 along the side which is opposite from angle B, which would be that side over there, right? Now we've got 2 of the 3 side lengths in the triangle. To come up with the cosine of angle B, we're going to need the adjacent side, which we don't have, but we can find, once again, using the Pythagorean theorem, right? Call this side A if we want to, and A squared plus 5 squared is equal to 13 squared. Do that little bit of algebra to come up with A is equal to 12. And so now we can write the value of the cosine of angle B. Again, it's the adjacent side, which we just found out was 12, divided by the hypotenuse, which is 13. Okay. And once again, 12/13 is the value of the cosine of angle B. It is not the number of degrees in angle B itself. Okay. Moving on. Number 9, find the tangent of angle Q from the triangle below. If we were in class, I'd ask you to do this on your own. Maybe you want to pause this video, try this problem on your own. Go ahead. This one's a lot like number 7. Okay, the tangent, SOHCAHTOA. Let's see, tangent is opposite over adjacent. From angle Q's point of view, put yourself there. The opposite is this one. Oh, we're going to have to find that out. The adjacent is the 4. So I'm going to have to use a little Pythagorean theorem here again. 4 squared plus b squared is equal to 9 squared. Blah, blah, blah. B squared is equal to 65. And so b is equal to the square root of 65, which cannot be simplified. Don't turn it into a decimal. Okay. So the tangent of angle Q, once again, is the opposite divided by the adjacent. The opposite side, we just figured out what that is. It's the square root of 65. And the adjacent side was given to be 4. Okay. Last problem, number 10. This is a lot like problem number 8. No. Oh, do I not have a? Oh, this one's new. Good. I thought we'd already done one like this. Okay, I didn't even draw a picture for this one. And there are 3 or 4 homework problems like this. No picture at all. Angle E, what angle E? Where angle E? You've got to draw a picture for yourself. You need to draw a right triangle. And it doesn't matter which way the right triangle is facing, right? It could be laying down like this one in numbers 7 and 8. It could be pointing down like that one in number 9. It could be standing up tall like that. It doesn't matter. I tend to draw all my triangles for problems like these kind of the same way, but it really doesn't matter. Draw a right triangle and make it look like a right triangle. Don't be sloppy about this. Don't draw a triangle like that and like put a right angle over it. That does not look like a right triangle. Okay. And then you might confuse yourself as to where the hypotenuse is. And then make one of the acute angles angle E. Keep in mind, for this course, for this geometry course, these angle inputs must always be acute angles. So you cannot put the E here, okay? You can put it along either one of the other 2 angles. It won't matter, okay? I tend to always put it down there in the lower left corner. Now you've got to put these lengths into your picture, okay? Let's see, SOHCAHTOA. See how often I keep going back to this? I mean, if you have to look this up every time, it's going to get frustrating and time consuming. Let's see, cosine, this 3-letter block here. Cosine is equal to adjacent over hypotenuse. So from angle E's point of view, the adjacent side is this one. That has to be the square root of 3. And the hypotenuse is 2. So that's where those numbers go. Okay? You got to draw the picture. I've got some homework problems like this. Now to find the sine, going back to SOHCAHTOA, sine is opposite over hypotenuse. And from E's point of view, the opposite is, oh, go figure. Isn't that always the case? The one side that we don't have. Give it a variable name. Do your Pythagorean theorem. A squared plus the square root of 3 squared equals 2 squared. What is the square root of 3 squared? Square root of 3 times the square root of 3. That's the square root of 9. That's just 3. A squared plus 3 is equal to 4. Subtract 3 from both sides. A squared is equal to 1. Square root of both sides. A is equal to 1. Now we can answer the question, which is what was the value of the sine of angle E? It was the opposite, which we just found. The opposite is 1 divided by the hypotenuse. Sine is opposite divided by hypotenuse. That's what SOHCAHTOA helps us remember. The hypotenuse is 2. Okay, there's the answer to that question. You're not going to encounter anything in the homework that isn't just like all the problems that we worked out. So in that sense, it's pretty straightforward. But there's a lot of brand new terminology here, and it's going to take some getting used to. So don't skip out on the homework. Don't do 3 or 4 problems and think, I got this. Not a good idea. Do them all, check the answers. And if anything's not making sense to you, reach out to me or whoever your teacher is to get your confusion straightened out. All right? See you next time.